In this session, we're going to see about polynomial inequalities, which are going to feel a lot like quadratic inequalities, but as it turns out, are less predictable. If we consider the graph of a polynomial function, and I'm just going to draw just kind of a generic one here. It starts in the third quadrant, goes up into the second, bounces off of the x-axis, and then we end up with a y-intercept. Let's cruise back down here. Oh, look, it wiggled. Didn't even mean for it to. Here we have, let's say the x-intercepts are at a0, b0 where it bounced, and then c0. And I don't really care about the y-intercept right now. What we have are function values, some of which are positive. Those are the ones that are above the x-axis. Some of which are negative. Those are below the x-axis. And the ones on the x-axis, of course, give us 0 function values. Any part of the graph that is above the x-axis then has a positive function value. And so we can write down the intervals over which this occurs. If we name this function f, then we can say that f of x is greater than 0 on the intervals from a to b and union from b to c, because at b it's equal to 0, right? So that's due to the non-strict inequality, right? We aren't including b there. And any part of the function that is below the x-axis indicates that we have negative function values. So f of x is less than 0 on the intervals from negative infinity to a, and then from c to infinity. Don't confuse this with increasing and decreasing. We aren't looking at whether the function itself is increasing or decreasing. We're concerned with whether the function values are positive or negative. Let's make a side note here. If we were looking at, say, for instance, f of x is greater than or equal to 0, then we would say that that's true on the closed interval, square brackets, from a all the way to c. You see, because those are values where the function is either positive or 0. Now, because polynomial functions are continuous and behave themselves, we don't have graphs switching from negative to positive unless they go through 0. And so this outlines our general strategy, which is going to be find zeros, pick test points that we will use to evaluate the function to figure out if it's positive or negative in intervals defined by the zeros. And then we're going to write down the intervals that give the solutions to the inequality. Let's get started. Solve x times the quantity of x minus 1 squared times the quantity of x minus 3 is less than 0. And we're to give our answer in interval notation. I want to distinguish again from solving equations. We did this with quadratic inequalities. We're going to do it again with polynomial inequalities. We do not set x less than 0, x minus 1 less than 0, and x minus 3 less than 0. That does not work for inequalities. We need to be concerned with how the factors interact with each other. What I do get, though, is the zeros from the factors. That doesn't really change. So I'm going to draw an x-axis here because our variable is x. I'm going to put marks at 0, 1, and 3 because that's where the expression is equal to 0. Now what I want to do is I want to pick test points. I want numbers that are not the ones I just mentioned. I want numbers to the left and to the right of those zeros. In other words, in the intervals defined by those numbers. So I need a test point to the left of 0. Seems to me that, I don't know, x equals negative 2 would be a good test point that's negative. Between 0 and 1, kind of sucks. We're going to use x equals 1/2 as a test point. Between 1 and 3, oh, x equals 2 looks good. And just to think outside the box, the interval to the right of 3, I'm going to say x is equal to 10. What we're going to do is we're going to consider kind of what would happen with an xy table, although I'm not going to actually figure out what the values are. Our inputs are what I just mentioned, those test points, -2, 1/2, 2, and 10. And what we're going to do is we're going to consider each factor with these particular x values. So if we first consider -2, -2 as the factor x is a negative factor. -2 in place of x for x minus 1, the quantity squared, well, that factor is never negative. -2 in place of x for x minus 3 would give me a negative factor. And so with -2 as an input, we have negative times positive times negative. That is going to be a positive output. Because of the continuity of a polynomial function, every value to the left of 0 is going to give a positive output. Next, we have x equals 1/2. The factor x is going to be positive if x is 1/2. X minus 1, the quantity squared, is always positive because it's squared, or it could be 0. And 1/2 in place of x for x minus 3 is a negative factor. Positive times negative is a negative output. That's going to be the case for every value between 0 and 1. And so I mark that that's negative in that interval. For x equals 2 as an input, the first factor is positive. The second factor, being squared, is always positive, or never negative. The third factor, if we had 2 minus 3, it's going to give me a negative. And so that's a negative output, positive times negative. Therefore, between 1 and 3, I know that all the outputs are going to be negative. Finally, for the input 10, the first factor is positive. The second factor, being squared, is always positive. And then the third factor, x minus 3, if x is 10, is positive. Positive times positive is positive. And that'll be the nature of all of the input values to the right of 3. Now I know intervals where the expression is positive and where it's negative. And I look back at the original inequality. We were looking for where the expression was less than 0, which means I'm after the intervals where we had negative outputs. Since it's not or equal to 0, I'm going to use parentheses at the endpoints. And so our intervals are 0 to 1 and 1 to 3. And because those are two distinct separate intervals, we're using a union to connect them. That's our solution. Next, we have solve x cubed plus 7x squared minus 36 is greater than or equal to 0, giving our answer in interval notation. Our strategy: find zeros, pick test points, write intervals. Finding zeros in this case is a little more interesting. Here we have a polynomial expression. And so, as you may recall, what we need are factors of 36 divided by factors of 1 to give us a list of possible zeros of 1, 2, 3, 4, 6, 9, 12, 18, and 36. And as you hopefully recall, what we do is we guess from this list using all of our tools and synthetic division. I'm going to go ahead and use a 2. Now our coefficients for x cubed, it's 1. For x squared, it's 7. There is no x term, so don't forget that 0. And then finally negative 36. And now using synthetic division, I bring down the first one and then multiply and add. So 1 times 2 is 2 plus 7 is 9. 2 times 9 is 18. Bring down that 18 because you add it to 0. 2 times 18 being 36 gives me 0. And so I now have x minus 2 as a factor. Since the quotient has coefficients of 1, 9, and 18, I know that we're looking at x squared plus 9x plus 18. And so that product is greater than or equal to 0. That's what we're after. As it happens, x squared plus 9x plus 18 factors. So we're looking at x minus 2 times x plus 3 times x plus 6 is greater than or equal to 0. And we're again going to lay this out using a number line. And I'm going to use x as the variable because, it is. I'll mark -6, -3, and 2. And now test points. I'm going to use -10 to the left of 6, -5 between -6 and -3, 0 between -3 and 2, and then 7 to the right of 2. Actually, you're going to do that. What I'd like for you to do is, using the factors x minus 2, x plus 3, x plus 6, and the test points that we just identified, -10, -5, 0, and 7, figure out whether each input gives a positive or negative output. So go ahead and pause the video, crank those out. So I get that for -10 as an input, I have negative output. Same thing for 0. So I'm just going to write negative to the left of -6 and between -3 and 2. I have positive outputs associated with -5 and 7. And so I know that the expression is positive between -6 and -3 and to the right of 2. Because the original inequality was greater than or equal to 0, I'm after the intervals that are positive, but I want to include the endpoints where possible. So the solution to this inequality is going to be square bracket -6 comma -3, square bracket at -3, union, because they're two distinct intervals, square bracket 2 comma infinity. Infinity always gives a parenthesis, and there it is. I want to make 2 points before we are done with this. We started out with the inequality x cubed plus 7x squared minus 36 is greater than or equal to 0. Suppose we had started out with x cubed plus 7x squared is greater than or equal to 36. What we would first want to do is subtract 36 from both sides so that we are comparing values with 0. If we look at what we did with our factors, it was much easier to see if something was positive or negative than to see if it was, say, bigger than or less than 36. Besides, this is how we find the zeros. We have to have an inequality that has 0 on one side. So I want to make one last consideration that maybe puts a little bit of context and possibly meaning to what we've just done. Suppose we had a function f of x is equal to the square root of x cubed plus 7x squared minus 36. And suppose I wanted to know the domain of this function. I would be looking for values that don't make the radicand negative, right? In other words, I would want values, x, such that x cubed plus 7x squared minus 36 was greater than or equal to 0. So in this case, we would have a polynomial inequality as a result of trying to understand something about a completely different function. Just be aware that it happens like that sometimes.